So we've proved the fundamental theorem of calculus, which says that if you have a continuous function that contains some fixed x value a, then the area function that you can build out of that continuous function f is actually an antiderivative for f. So this is essentially a derivative rule for area functions. A couple important things to note about this is the bottom bound has to be a constant. So x is the variable in here, and we aren't changing a, we're only changing x. So the bottom bound has to be a constant if you want to use the fundamental theorem of calculus. Also, notice that the top bound in this integral is just the variable itself, x. It's not some function of x, it's just x itself. So if you want to use this, theorem, the top bound has to be x. And then inside is no x's, right? Just your dummy variable, whatever it happens to be, t in this case. All right, with that in mind, let's look at some examples. So first, let's find the derivative of this function. So I haven't given this function a name, but we could, if we wanted to, we could call this a of x. So let's find the derivative of this function. So the derivative of the integral from 1 to x of cosine of t squared dt. All right, well, we're taking the derivative of an area function, so we should definitely think about using the fundamental theorem of calculus. But remember, the fundamental theorem of calculus has two caveats. The bottom bound in your integral has to be a constant, and it is. And the top bound in your integral has to be just the variable, right? And the variable is x, and our top bound is just the variable, and there are no other x's. So we can use the fundamental theorem of calculus. Now, the fundamental theorem of calculus says if you take the derivative of the area function, you get the function you started with. Well, what is the function we started with? It's the function inside. It's this function, cosine of something squared. Right? This is the function that our area function was built out of. Right? This is sort of playing the role of f. So the fundamental theorem of calculus says that the derivative, if you start with this function, cosine of something squared, you build an area function and then take its derivative, you get the same function back. Right? We should put x in here because x is the independent variable. So the derivative of this area function is just cosine of x squared. All right, fair enough. Let's look at another example. How about finding the derivative of this area function? So derivative with respect to x of the integral from x to minus 1 of the square root of, oops, I have a typo here. I meant for this x to be a 2. Okay, so square root of t squared plus 1 dt. Okay, so we're differentiating an area function, so we should definitely think about using the fundamental theorem of calculus, but the bottom bound isn't just a number. The bottom bound is a variable this time, so that's a problem. And also the top bound isn't the variable, the top bound is just a number. So it's as if these two are backwards, right? We can't use the fundamental theorem of calculus directly because the bounds are in the wrong place. But one of the properties of integrals that we noticed is that if you want to, you can switch the bounds as long as you put on an extra minus sign. So here we would like to switch the bounds, so let's do it. So before we calculate this derivative, we're going to adjust the stuff inside. We're going to switch the bounds and also put a minus sign on. Square root of t squared plus 1. Okay, so now the function we're taking the derivative of is the same, it just we're writing it different for our own purposes. All right, so now we can calculate a derivative. Well, we have a constant multiple here in our function that we're going to differentiate, so we can move that outside. And the stuff that's left over, now we can use the fundamental theorem of calculus. So the fundamental theorem of calculus says, well, don't forget this minus sign, but the fundamental theorem of calculus says when you differentiate the area function, you get the function you started with. So that's the square root of x squared plus 1. All right, and we're done. One last example. Let's find the derivative of this crazy thing. The derivative with respect to x of the integral from 0 to sine x of t squared plus 2. I must have had squares on the mind when I wrote these examples. Okay, so we're going to use the fundamental theorem of calculus at some point, but the bottom bound is a constant, so that's good. But the top bound is not just the variable x, it's actually some other thing. It's a function of x, right? So we can't use the fundamental theorem of calculus directly. So how can we handle this? Well, let's see. How is this put together? This is actually, this function that we're trying to differentiate, it's a composition. It's a composition of this area function, so integral from 0 to something of t squared plus 2 dt. It's this function composed with the function sine of x. Right? Composition is just a fancy name for putting one function into another function. So this function is a composition. And what derivative rule do you use for a composition? Well, you use the chain rule. So let's use the chain rule. So the chain rule says you take the derivative of the outside part. So what is the derivative of this function? Just the area function. Well, that we can use the fundamental theorem of calculus to find the derivative of this simplified area function. It says that it's, the derivative is something squared plus 2. And then the chain rule says two more things. You multiply by the derivative of the outside function and the derivative of, the derivative of the inside function. And the derivative of sine of x is cosine x. And also, the chain rule says that you have to take the inside part and put it into the derivative of the outside part. So we have to put sine of x in here. All right, so to clean this up a little bit, I guess you'd write sine squared x plus 2 times cosine x. So there is our derivative, right? This piece sort of corresponds to the derivative of the integral part, and this piece is from the chain rule because we had sine x in here instead of just x. So the fundamental theorem of calculus gives us a tool for calculating derivatives of these area functions, but you do have to be careful about the restrictions that the fundamental theorem of calculus has. The bottom bound has to be a constant, and the top bound has to be just the variable. If it's not just the variable, you're going to end up using the chain rule.